Salam sejahtera and a good day. This session is about populations and samples. We'll be reviewing important points on what are actually populations, which forms the basis from which we sample our samples from, and then we shall be talking about how this actually eventually applied to a population survey. Now, what is population? Population is actually a defined group of individuals or entity. It comprises of all sampling units that are actually or potentially available for description. So that means if you are designing a study, all sampling units that are eligible for your study will be the samples. And it is defined, the population is defined by species, time, location. By location, I mean area or habitat. So it is actually a precisely described entity from which a study draw its samples from. For example, all the LID cattle or local Indian dairy cattle within the Selangor state during the survey. Or it can also be transcribed and expressed in the formula form as per the Bernoulli's equation, where the variance of a population can be described as P bracket 1 minus P over the total number of samples. And then from population, then we move on to statistical population. So statistical population very much depends on what we are researching. And oftentimes we are comparing characteristics of a statistical population to another statistical population. This is in fact the main reason why we conduct statistical tests. For example, milk yield in a primiparous cows, versus multiparous cows. And in this case, primiparous cows means cows that had just delivered their first calf, whereas multiparous cows refers to cows that had calved more than once. So it makes sense for us to compare cows, milk production in cows that produced their first calf versus cows that have calved multiple times. So in this case, this kind of definition allow us to define the sampling unit. In most circumstances, we will typically refer this as a population rather than the general population, because by defining it as general population, it seems a little bit overreach. Let's look at all these questions on sampling unit and their related statistical population in detail. For example, if you're asking about what proportion of a LID are females, then your sampling unit will be an individual animal. Your statistical population then will be all the LID cattle in the Selangor state. Then if your question is actually on the proportion of cows lactating, then the sampling unit, in order to determine what is the proportion of cows lactating, will be an individual cow. In this case, the relevant statistical population will be all the LID cows only. And to go deeper, in order to determine what is the average milk yield per cow, since not all cows are producing, so our sampling unit to differentiate this will be an individual lactating cow. This will allow us to differentiate between cows that are not producing milk from cows that are producing milk. So in this case, the statistical population will be all the lactating cows only, since all the lactating cows are the one that fits our definition of the sampling unit. And finally, if our statistical question, our research question is actually on the average milk yield in multiparous cows, then the sampling unit for it will be an individual lactating and multiparous cows. So in this case, statistical population will be all the lactating and multiparous cows only. So you can see this in fact is actually a relationship between the sampling unit and statistical population, where the definition of the statistical population take after what we redefine for each of the sampling unit. In that sense, the two basic aims of the sampling units are the two basic aims of sampling are, number one, to have a sample which is truly representative of the actual population with high confidence. And number two, to have a high ability to detect actual effects. In statistical speak, high confidence is equal to 1 minus alpha. So in this case, alpha is actually the significance level. So you can say that fact number one is actually referring to confidence level. So because when you have 1 minus alpha and alpha equals 0.05, you end up with 0.95 or a 95% confidence level, which is typical application for biological sciences. And then to have a high ability or power to detect the actual effects refers to 1 minus a beta. Beta is actually a quantity that is supposed to be read together with the confidence level. In this case, it refers to power. And power refers to the ability to detect an effect when the effect is actually there. So based on that, we really need to look deeper into what is actually sampling unit. A sampling unit is actually a basic unit on which observations or measurements are made. The number of sampling units is expressed as the small n, and a collection of sampling units are known as a sample, or typically known as group, denoted by K. This is unfortunately often abused, consciously or subconsciously. As you can see in the following example here, you can have a sample comprising of rat cages with 3 rats each versus rat cages with a single rat. Glass aquariums with 20 fish each versus glass aquariums with a single fish. And cages with 5 broiler chickens each, litter of piglets, puppies, or kittens. What is more important is that you really need to know the nature of experiment. If let's say you conducted a trial whereby the rats are not interfering with each other, then it is fine for you to calculate each rat within that rat cage of 3 rats as an individual sampling unit. However, if the rats are interfering with each other, then you are better off counting rat cages with a single rat as the eligible sampling unit. Why is this so? Imagine you're running a nutrition trial whereby each rat in the cage is allowed free access. So if you were to put 3 rats in the cage and everybody will have free access to food, there will be bound to be a situation whereby the dominant rat will eat more, whereas the submissive one may got uh, less than what they are typically entitled for. And in terms of treatments equality, this is actually an issue if you are designing experiments where each individual are supposed to have the same exposure to treatments. Conversely, if you were to dose those animal, those animal or force feed the animal individually, then there is a situation whereby the presence of one rat will not interfere with the other rats in the same cage, even though they are house 3 rats each. So under those circumstances, we can still count each rat as an individual sampling unit, even though you are keeping 3 rats each. In the scenario whereby you cannot avoid one rat interfering with another rat when they are put together in a cage, it is often best to isolate those animals and put them singly in a single cage. So as you can see here, it very much depends on your purpose and the dynamics of your trial, the nature of your trial. So if your trial involves a situation whereby each sample or each sampling unit has the ability to interfere with each other, it is best to isolate and separate each of the sampling unit. Now that brings us to the next question, a replication. A sample should have more than one sampling unit or replicate. It is done because to minimize variation within sampling units. Because in this case, it will approximate the population average as the sample size grows. This is important if you're running nutrition and field biology experiments. This is also done to increase the reliability of estimates, because if you have more replicates, then the size of the standard error and standard deviation will be more predictable and stable. And when you have SE and SD, you will also provide a measure of variability of statistical tests. And replicates should be independent from each other. Well, you can look at these 2 examples here. 6 germinating seeds within a single petri dish versus 1 germinating seed in 6 petri dishes. This is more or less similar to our discussion on sampling units held earlier on the earlier slides. Or you can have another scenario whereby you're measuring fat content 10 times in a single milk sample versus one fat content measurement from 10 milk samples. In the prior example, you are talking about pseudo replication. That means replication, which is actually forced upon a single sample. And therefore, it doesn't have independence versus a latter sample, whereby you are measuring one fat content measurement from 10 milk samples. That is actually independence because you have a fat content from each of the 10 milk samples to constitute the average of those 10 milk samples. This holds true because replicates should have minimal or no interference with each other. So in that case, please look at your trial to ensure that each animal within the trial or each individual within the trial do not have the ability to interfere with each other's treatment. As you can see in the following examples here, involving the ram, involving an active animal, or a fast-growing plant. In terms of sampling, samples, as I mentioned earlier, must be representative of the base population that they represent. The sampling methods that can be employed include simple random sampling, whereby each sample has an equal chance to be selected. Systematic sampling, whereby you'll be selecting sample members at fixed interval. It could be intervals in terms of the counts or intervals in terms of a distance. But be aware that when you have systematic sampling, you may introduce systematic errors. The third strategy will be stratified sampling, whereby you are dividing the population into subgroups and then randomly selecting from among those groups. For example, you may want to have stratified the samples according to their age and then further divide them according to their male, female, and then maybe their body weight and so on and so forth. As you can see, systematic sampling to some extent, you may have, stratified sampling, you may have an issue of a narrower sampling pool. And apart from that, okay, on stratified sampling, when you are dividing the population into subgroups, you are going to have an issue with proportional representation, and therefore there are actually specific formulas that you can actually follow. Now, next to stratified sampling will be cluster sampling. This is a case where groups are selected rather than individuals. For example, you randomly select 5 farms from among 25 farms in a district. And a cluster is preferred because members within a cluster are judged to be homogeneous. The final option for sampling, which is actually incidental or convenient sampling, is actually not really an effective sampling method at all, and therefore not recommended because it has no way to quantitate bias. Now let's look at the typical formula that can be used for simple random sampling. So the formula for random sampling can be calculated based on either the total samples, the mean that you are intending to have, or the proportion. So in this case, this is actually as depicted as per the formula. And let's look at the example one by one. Example application number 1. For example, you want to estimate the mean body weight of sheep on a farm. We anticipate that the standard deviation of the body weight in sheep of this age is around 40 kilogram. We would like to be 95% certain that our estimate is within 10 kilogram of a true mean. So how many animals should we include in your sample? This is an estimate whereby you want to determine a value, a total, or anything else that you want to be accurate within allowable limit. In this case, we want to be 95% sure that your estimate is within 10 kilogram of the true mean. So in this case, you can see that by taking the formula for mean, then you can calculate all the numbers required. In this case, you need at least 61 animals. So in this case, the Z of 1.96 typically indicate to you that this is actually consistent with the Z score for 95% confidence level. The next example, we may want to estimate the seroprevalence of CLA in a population of goats. CLA is actually a disease, caseous lymphadenitis. The expected prevalence is 10%. Prevalence means how frequent this disease is to occur in a population. And we would like to take enough samples to be 95% sure again that our estimate is within 20% of the actual prevalence of disease. Now, bear in mind that this kind of estimation has its limits. It can only be done on disease with a prevalence of more than 10%, or maybe if you want to push it further, maybe more than 7 or 5%. Because if the prevalence is too low, then the estimates using these samples, this calculation will be definitely inaccurate. So in this case, how many animals should be included in a sample if you want to have a rough estimate of the seroprevalence of animals? So in this case, based on the calculation, as you can see here, Z-score again is 1.96, corresponding to 95% confidence level. Then you are going to need at least 864 goats. So in this case, the PY is actually 0.1. 0.1 denotes the prevalence that you are expecting. And what you are doing here is actually you are calculating the derived seroprevalence expected within a population. So in this case, again, you also have to remember simple random sampling may not be applicable at all times because not all factors acted equally or randomly within a population. Just imagine if you have 100 samples to be selected from, the first sample that you draw will have a chance of 1/100 to be drawn. By the time you reach to sample the second animal, the chances to be sampled will be 1 in 99. The third sample will be 1 in 98. And by the time you reach the 50th sample, it will be 1 in 50. So in this case, you can see that there will be an increasing chance for certain samples to be selected as more samples are being removed from the population pool. So in real life, simple random sampling may not be applicable at all. And furthermore, they are also distorted by factor interaction or other interaction confounding factors as well. And if you were to practice simple random sampling, another hurdle is that the potential sample numbers may be too big to be manageable. So it is common for us to stratify or group the samples into common groups. For example, you may want to stratify them by gender and then by age and so on and so forth. And this results in multi-stage sampling, which is actually applicable across a lot of disciplines. Multi-stage sampling can be done according to either a systematic sampling, a stratified sampling, and cluster sampling, which we already pointed out earlier. So systematic sampling, as I mentioned earlier, could be done either in intervals of distance or intervals of counts. Stratified sampling, as what we have discussed just now, it could be involving you subdividing them into smaller groups, as we already mentioned earlier. Whereas cluster sampling is actually, as what has been explained earlier, where you group samples of the same attributes to make them more homogeneous. Let's move on to the description of the samples itself. When you are sampling from the population, it's important for us to have an idea of description of variability. So this description of variability can be seen from a perspective of variance and standard error. And then, of course, it could also be described according to confidence limits. So this, in turn, gives us actually an estimate of their lower limits and upper limits, which is precisely what we need when we are actually estimating mean or estimating ranges based on 95% confidence interval or a 95% confidence level. As you can see here, based on 95% confidence interval, consider the following values from an experiment where the mean is 14.12, 12, and the standard error is actually 0.65. So how do you calculate the upper limit? The upper limit will then be the mean itself, 14.12 plus minus 1.96, which is actually the Z-score for 95% confidence level, and multiply by their standard error, 0.65. So in this case, 14.12 plus the product of 1.96 multiplied by 0.65 will be the upper limit. and 14.12 minus the product of 1.96 multiplied by 0.65 will give you the lower limit. And if you are referring to 99% confidence level, then you use a Z-score of 2.72. As you can see here, the same value, the mean 1.12, but if you are looking at 99% confidence level, the upper limit will be given by the product of 2.72 multiplied by 0.65 added to 14.12. So in this case, if you are looking at the lower limit of 99% confidence level, it will be 14.12 minus the product of 0.65 multiplied by 2.72. And obviously, this is actually from a small and normally distributed sample. And you can actually see and visualize how the confidence level decreases as the n increase. So you can see here, this tells you what? This tells you, in this case, the data derived from sample will be getting more and more reliable as you increase the sample size. And you can see here, the threshold occur somewhere between 100 to 200. So beyond 200, your confidence level will become much more stable, much more predictable, meaning that any further increase in sample size may not result in big and drastic increases in terms of the confidence level. So in this case, you can see that sample size below 100 doesn't give much info, and those beyond 1000 probably doesn't worth the extra effort because of the stability that you're going to see, due to the stability of mean that you're going to see because of the confidence limits. When I mean sample sizes below 100 doesn't give much info because of the high variability indicated here in this case. So as a rule of thumb, a sample of anything between 10 to 30% of population is required if the number is small, and 1% if it is big. Why? Because we just need to ensure that you exceed the threshold of at least 200 or 300 individuals to make sure that whatever confidence limits that you are calculating will be stable and representative of the samples itself. Now, if you were to sample from a population for a defined trait, there is actually a formula for it, which is actually given by Dell 2002. This formula is actually depicted on the screen. It is important if you are trying to determine the appropriate number of samples to perform to have a sufficient chance of getting your desired trait or goal. And based on that, the sample size can be estimated if the success or failure rate can be predicted. For example, you may have seen a trial saying that they are using 40 diabetic animals, 40 diabetic rats. So in order to arrive at that 40 diabetic rats, you may need to have a certain degree of normal rats to start off with, to perform certain procedures. And these procedures will have their own success rates. So if all these success rates can be defined, then you'll be able to calculate the starting sample size in order to arrive at that 40 diabetic rats. So in this case, it will involve calculating several properties. You can see here, it also involves test power, which is actually 1 minus beta here. And you can see here, it also wanted you to calculate what is the proportion of animals that did not have the desired goal. So in our case just now, since we only wanted animals with diabetes, so we need to calculate what is the proportion of animals that will not get diabetes despite your treatment in order to have your starting sample size. So it is actually given by n equals log beta divided by log p prime, where p prime is actually the proportion of animals that do not have the desired goal, and beta is actually the value that you can actually use to calculate the power of the test itself. Remember, power of the test is actually the ability of a test to detect an effect when the effect is actually there. Let's look at this application using that particular Dell's formula. So you assume that the success rates of producing a transgenic animal carrying an obesity OB gene is 5%, and investigator only have about 90% chance of getting the transgenic. So in this case, in order to produce one animal, what you can see is that you need 45 animals. So based on that, if you are going to propose a study comprising of 10 OB gene animals, you cannot start with 10 OB gene animals. You need to start with 10 multiplied by 45 animals, so 450 animals. So in this case, this is actually something that you really need to pay attention to every time when you refer to references or refer to the techniques that is being proposed by prior publication. Similarly, you can also use these techniques to look at how many animals that you need to test, assuming that need to test in order to rule in or rule out diseases. So assuming that you have 30% of the animals infected and the investigator need to have 95% chance of detecting a disease. So how many animals do you need to sample? The formula will tell you that you need 9 animals. You need to sample at least 9 animals. So this is actually something that you have to bear in mind as well. So this formula can be used to predict to calculate sample size required for an outcome, and at the same time, it can also be used to determine what would be the minimum number of animals that you need to sample for an outcome to be seen. And in the same manner, veterinarians are often asked to confirm the absence of diseases from a group of animals. So you can see here, this is actually based on the formula published by Stevenson, 2009 from Massey University. You can refer to the materials at epicentermassey.ac.nz. So in this case, how many animals do you need to test? From a herd of 2,000 animals, assuming the prevalence of disease is 25% and the test sensitivity of 100%. Remember that this formula assumes that the test has perfect ability to detect diseases, which is not the case at all. So oftentimes you only have what? 50, 60, 70, or even maybe 90 or 99% to detect the diseases, but never 100%. So as you can see here, it will require you to have huge numbers of animals to be tested in order to ensure whether a disease is completely absent from a group of animals. So again, this is actually adaptation of the formula that has been given earlier to rule in or to rule out a particular phenomenon. Finally, let's look at applications of a sampling or sampling error in public opinion polls. Remember, prior to this, we've been using the Z-score to multiply by SE in order to determine the error rate. Now, let's look at a real-life example from whatukThinks.org. This is actually a referendum conducted between 19 January to March, January 2021. This is actually asking the Scottish on what is their likelihood to remain, to join the European Union following their abrasive Brexit. So in this case, you can see that on average, the sample size calculated tells you that they need only about 1,000 people here in this particular study conducted in February. So how can we determine whether people are in favor of joining the EU or against joining the EU just by basing 1,000 or 1,200 people? So how do they calculate this and what will be the rationale? Now let's see. This is actually a classical example of Bernoulli's distribution. Remember at the first slide, we are able to predict the population variance using this particular formula. P multiplied by a bracket 1 minus P, where P is actually a proportion of saying agreeing to something, whereas 1 minus P is a proportion of saying you do not agree with something. So as you can see, this is actually a dichotomous type of equation where you only have yes and no. So in this case, if you set the sampling error is about 4%, then based on 95% confidence level, the lower percentage limit will be minus 1.96. Again, remember this is a Z-score multiplied by the SE derived from the population variance. And the upper percentage limit will be expressed equally. Now, let's calculate what will be the samples that you require when you are estimating at 4% error. So at 4% error, you need about 1,200 samples to account for upper limit, that means plus 1.96, and lower limit means minus 1.96, so plus 4% error and minus 4% error. So you need 1,200 subjects. At 3% error, you need plus minus 3% error, you need 2,134 respondents. At 1% error, you need 19,208 respondents. So this is actually one reason why the prior study oftentimes start with anything between 1,000 to 2,000, and then they say that the sampling, the opinion polls, and so on and so forth, typically we have an error rate of about 4%, 3%, and so on and so forth, as you can see in our calculation here. Then you have to ask yourself again, is this 4% error, 3% error accurate, representative, and can it be manipulated? Okay, can it be manipulated? So these are the kind of things that you need to be mindful as well. Because why? How can 1,200 people or 1,000 respondents provide an accurate view of what is going to become of a national decision to join the EU or not to join the EU? And this also opens the possibility that for some of this interpretation to be manipulated and hijacked. So in this case, you can actually manipulate this by selecting a population base who are actually overwhelmingly pro-EU or against EU, and then you can publish a result saying that everybody actually agrees to join EU or everybody actually disagrees to join EU. So in this case, it is the onus of the surveyor himself or herself to ensure that you are selecting an unbiased sample. And this is actually something that we really need to take care in executing when you are conducting public opinion polls. Otherwise, we could be believing and subscribing to the erroneous outcome of public opinion polls.